Hello everyone, I am Aadarsh Pathak. I am currently a PhD student at Melbourne University. I'm sorry. Working with Stuart Wiley, and I worked on an analytic model predictions for emission line galaxy properties for high redshifts, and today I will discuss about that project. So let's dive into this. Okay, before going into the details of the model, it's it's a good thing to start with this picture. So here you can see the evolution of our universe on the left hand side to the current present universe, which we see today. The reason or the regime which I'm interested in lies somewhere around here, which is the epoch of reionizations. So as we all know that this is the phase when neutralizium turned into an ionized one. So I'm looking at emission line galaxies situated at somewhere here. So what are these emission line galaxies? So we all know that this is the galaxy. These are the galaxies which emit emission lines, and these emission lines are being generated in their surrounding gas when collisional excitation or radiative transfer or some kind of physics takes place. So we basically observe some kind of a spectrum like this with emissions. But there is a problem is that basically before JWST, we had a very limited information about the physical properties of these high redshift emission line galaxies because we were mostly relied on photometric data and they had lots of contaminations in the optical emission lines. But thanks to JWST now, we have a tremendous amount of data and we can go deeper and deeper with more spectroscopically confirmed redshifts. One of the JWST survey, which is particularly dedicated to the epoch of reionization, is a FRESCO survey. So it stands for First Reionization Epoch Spectroscopic Complete Observation. So it is going to observe 4 to 5 micrometers of a spectrum in its every field of view. And it will cover 260 arc-minute square field in extragalactic legacy fields of goods north and goods south with a NIRCam F444W filter. Though it's covering entire redshift range from 1 to 9, I focused on redshift ranging from 7 to 9, which you can see here in green color. And the possible emission line which we could get from that is W ionized oxygen and H beta line. So what I did, I basically try to make a model which can incorporate properties of these galaxies. So there were 4 key steps I involved in my analysis. I started with a simple analytic model where I picked a star formation rate density function model. And then I put some ingredients in the form of some physical properties of those galaxies. I calculated line luminosities, flux ratios for those galaxies. And finally, I calculated luminosity functions and number counts. So these are the 4 basic steps. So let's dive into the first step. So I just picked up a model which was originally proposed by Wiley and Loeb in 2012. So it consists of a galactic disk which is vertically supported by hydrostatic equilibrium, assuming gas at 10,000 Kelvin. This disk has some radius, scale height, and scale radius, as you can see here. And this disk can undergo major mergers and supernova feedback effect. And the model assumes that the supernova feedback can suppress the star formation in low mass galaxies. So this supernova feedback prescription is basically based on galactic porosity model, which was uh, proposed by Clark and Oy back in 2002. So they assume that we have a galactic disk and this supernova basically forms super bubbles inside this galactic disk, which can have some radius RE. So the model basically compares the radius of this superbubble with the scale height of the disk in order to infer what fraction of supernova energy is going to be used up as a feedback. So if it is lesser than the scale height, then the fraction will be FSN. Or if it is greater than the scale height, that means if superbubble breaks out, then it will be lesser fraction, either FD or FT. So these fractions are incorporated in star formation efficiency, which we can see here, and which can ultimately be used to calculate our star formation rate, and finally the star formation rate density function depending upon the press sector mass function and star formation rate. So this is the plot of the star formation rate density function. So here I'm plotting star formation rate density on the y-axis with respect to the star formation rate. So you can basically have an idea of how many galaxies we are going to observe per megaparsec cube per days. And you can see that it matches quite well with the observation. So it was the good step to go forward. Then the next step was to implement some physical properties. For that, we started with implementing turbulence velocities first, because as we know that as we go to high redshift, star formation rate increases, which can lead to more turbulent disk. Even the accretions are more prominent at high rate shifts. So in our analysis, we just simply assume two basic turbulent drivers. First is when the turbulence is driven by accretion. So here you can see it is dependent on so many parameters like mass accretion rate, like turbulence efficiency, and so on. If you want to go into the details of each parameter, either you can contact me later on, or you can go into this paper from where I've derived this formula. And another one is the when the turbulence is driven by feedback. So here it is dependent upon the supernova rate density, scale height of the disk, and so many things. So if you look at the plot here I'm plotting the turbulent velocity with respect to the halo mass. You can see that the dash dotted line here represents the turbulent velocity when because of the accretion, and it evolves linearly with the halo mass, which is quite expected because for high halo mass we can expect high accretion rate. And this dashed line represents the turbulent velocity because of the feedback. So what we do, we basically take the net velocity effect from both of these accretions when we implemented in our model to calculate the rest of the physical properties. So the few of the physical properties we calculated are as follows. The first one is the ionization parameter. So as we know that it represents the ionization state of the ISM, how the ionizing gas is interacting with your ionizing source. By formula, it is just the ratio of number of ionizing photons with respect to the number density of particles. So if Q star is the photons per second, which is calculated from our super bubble, which I was discussing, having some certain star formation rate, and NP is our number density. And here's the plot of ionization parameter which I got. So for different redshift ranges, and you can see that it is evolving with the star formation rate, which is also mentioned in many of the literatures. And also you can notice here that the solid lines representing the case when turbulence is taken into account, and dashed lines represents the case when turbulence is not there. So you can see that the turbulence can lower the value of ionization parameter. If I'm not considering turbulence, the ionization parameter could have high value because of the high number densities we expect at high rates because of the compactness of galactic disks. So, in spite of other than ionization parameter, the other parameters are also affected by the turbulence. So, if you look at the pressure or number density, both of these are getting lowered because of the effect of turbulence, which is shown by the solid lines here. So these were the few physical properties. Apart from that, I also calculated galactic chemical evolution in order to calculate line luminosity, which I'll disclose later on. So for my simple analysis, I just used a closed box model where no inflow and outflow of gas is considered. We just consider that what amount of gas is present at any time in a disk with respect to the amount of gas present initially. So it depends upon your disk mass and stellar mass. And eventually stellar mass is dependent on star formation efficiency, which goes like this. So here I'm plotting total star formation efficiency with respect to star formation rate. And as I mentioned earlier that in the model, low mass galaxies are being suppressed because of the supernova feedback. So we can say that we have low star formation efficiency here. So when I plot gas phase metallicity, it shows almost similar kind of evolution as we saw in the star formation efficiency. So these were the physical properties I calculated. Now the next step was to calculate the emission line luminosity, because as I discussed, I'm looking at for Fresco's data for future. So basically Fresco will look at redshift 7 to 9, and for 4 to 5 micron spectrum, they are going to observe this doubly ionized oxygen. So here is the energy, five energy levels of the doubly ionized oxygen, and I'm considering this emission line here, which is and formula I have derived here, which is taken from the Youngs and Lees. They have done for different wavelength, 88.36 micrometer. I'm doing for different one. So basically, this emission line is dependent on two main stuff. First one is the gas phase metallicity, and another one is the ionizing photon luminosity, which I'm showing variation with the stellar mass here. So this is the plot of my line luminosity which varies with the star formation rate. So we can see clearly that it is varying linearly with the star formation rate. And as this ionizing photon luminosity is dependent on star formation rate, and I was discussing that I calculated ionization parameter from the super bubbles ionizing photon luminosity. So somehow ionization parameter also correlates with the star formation rate. Apart from that, I also calculated double flux ratio of O3 by H beta, since they are going to be the observables. So I used mappings, photoionization modeling code to calculate. And these O3 by H beta ratios are very much dependent on ionization parameter, pressure, metallicity stuff. So, and as I discussed already, that for turbulent case, these things are lowered. And that's why you can see here that for turbulent cases, we have a lower value of O3 by H beta as compared to the non-turbulent one. Okay, so then finally I calculated luminosity function here, which I'm showing you. So here I plotted luminosity function with respect to the log LO3. And as we can see, here I have plotted two different cases. One when I'm not considering any scatter, and the another when I'm considering a scatter. So as at high redshift, we can expect a scatter because of certain kind of uncertainties or so and it matches quite well with the observations also. And then finally, after based on our luminosity function, I calculated how many galaxies we are going to observe for the FRESCO survey for redshift range of 7 to 9 and for the given area. And for now, we believe that it will be around 330 to 400 galaxies which we can observe. That's all. With this, I can come to my conclusion. So I basically tried to make analytical predictions for emission line galaxies at high redshifts. I used the star formation model proposed by Vaidhi and Loeb. Then I calculated various physical properties associated with disk. And finally, on the basis of that, I calculated luminosity functions, flux ratios, and number count. That's all. Thank you.
You mentioned ionizing efficiency. So are you going to get access to FRESCO data, and will you try and constrain potentially reionization parameters?
Yes. So now FRESCO data is available. So next plan is to go into the FRESCO data and look at how we can differentiate between turbulent and non-turbulent disk based on the FRESCO data. And this is our future plan.